Before quantum theory, the world was believed to be a machine. Every falling apple, each ripple across the pond, moved with precise cause and consequence. This was the realm of classical physics, clockwork certainty, laid out by Newton and polished by Maxwell and others. But at the turn of the 20th century, this elegant machine began to stutter. It started, oddly enough, with something as commonplace as a glowing metal. In the late 1800s, physicists studied how objects emit light when heated, the soft red glow of a stove, the white radiance of molten iron. This study of blackbody radiation, as it was called, baffled scientists. The equations predicted that as the temperature increased, the energy radiated should rise infinitely at shorter wavelengths, a divergence known ominously as the ultraviolet catastrophe. But nature had no such catastrophe. Enter Max Planck, a man of deep conviction and quiet mathematical grace. In 1900, he proposed something radical to solve the paradox. Instead of energy flowing smoothly and continuously, he imagined it coming in tiny, indivisible packets, quanta. Energy, he said, was like coins instead of a stream. You could only spend it in specific amounts. He didn't understand why this worked. It simply did. Planck thought it a clever trick, a desperate fix. He didn't yet know he'd cracked open the gates to an entirely new realm of physics. A few years later, Albert Einstein, then a young patent clerk, picked up this idea and hurled it into the heart of light itself. He proposed that light could behave not only as a wave, but as discrete particles, later called photons. This explained something that had puzzled scientists for years: the photoelectric effect, where light knocks electrons off a metal surface only if the light has a high enough frequency. According to classical theory, brightness should matter. But it didn't. Frequency did. Einstein's insight won him a Nobel Prize and nudged light off its classical pedestal. Now it seemed that the universe was not only built from waves, but from particles as well. Or perhaps both? The questions multiplied. Niels Bohr, a Danish physicist with a poetic soul, tried to make sense of atomic structure. The old model, like tiny solar systems with electrons orbiting the nucleus, couldn't explain the strange spectral lines emitted by hydrogen gas. Bohr introduced the idea that electrons could only occupy specific orbits, or energy levels, and could leap between them by absorbing or emitting quanta of light, like rungs on a ladder, but no in-betweens. This was a vision half particle, half magic. From these early steps, a mosaic began to form. Light was not just a wave. Matter was not just a particle. Motion wasn't deterministic. Instead of smooth predictability, there was a kind of cosmic probability. One glows with a special kind of defiance, the idea that light comes in particles. At the time, light is understood as a wave. The elegant experiments of the 1800s, diffraction, interference, polarization, have all but confirmed it. Waves explain everything, or so it seems. But something isn't adding up. When light falls upon certain metals, they eject electrons. This is known as the photoelectric effect. It's not a gentle process. It's abrupt, instantaneous. And strangely, it doesn't matter how bright the light is. What matters is its color, or more precisely, its frequency. Shine red light, and nothing happens. Shine blue light, and electrons fly free, even if the beam is faint. Classical physics has no satisfying answer. But Einstein, he looks at Max Planck's earlier idea, that energy is quantized, and dares to apply it to light itself. Perhaps, he says, light is not merely a wave. Perhaps it comes in tiny discrete packets of energy. He calls these quanta, later named photons. It's not just a new explanation. It's a revolution. In Einstein's view, each photon carries energy proportional to its frequency. When a high-frequency photon hits a metal surface, it delivers a jolt strong enough to liberate an electron. If the frequency is too low, no amount of photons, no matter how many or how bright, can knock an electron free. It's not about volume, it's about potency. This insight is subtle but profound. It means that light behaves like a particle in certain situations, a notion that collides with its well-documented wave behavior. For the first time, physicists are faced with the duality of light, wave and particle, coexistence in contradiction. Einstein doesn't merely suggest a new feature of light. He invites us to reconsider what it means to observe reality. The photon carries no mass. It moves at the universal speed limit. It doesn't rest. It doesn't age. And yet, it has energy. It can strike, provoke, and illuminate. The simplicity of the concept hides its strangeness. A particle of light? A flicker with form? At first, the scientific community hesitates. The wave theory of light is deeply entrenched, its mathematical roots woven through physics like golden thread. But experiments, persistent, provocative, begin to favor Einstein. His prediction of how the energy of ejected electrons depends on light frequency is confirmed with remarkable precision. The photoelectric effect becomes not just a mystery solved, but a turning point, one of the early confirmations of quantum behavior. And yet, strangely, Einstein himself remains skeptical of quantum theory as it evolves. While he opened the door to quantized light, he is uneasy with the uncertainty and indeterminism that follow. He believes in an orderly universe. He longs for clarity, for deterministic rules, the kind that underpin relativity. To him, quantum mechanics feels like a painting with missing brushstrokes. But this photon, this child of his thought, takes on a life far beyond its origins. It becomes the key to understanding atomic transitions, where electrons leap between energy levels, shedding photons like autumn leaves cast from a branch. It explains the behavior of lasers, those perfectly coherent beams that cut steel and perform eye surgery. It shapes cosmology, where photons journey from the birth of the universe, stretching into the gentle hiss of the cosmic microwave background. It fuels solar panels, converting sunlight into currents, powering our homes, our dreams, our futures. Through Einstein's photon, a new vision of light emerges, not as one thing or another, but as both. Not as a single explanation, but a shimmering dance of perspectives. And this duality extends. If light, this most wave-like of things, can be a particle, might particles also have wave-like properties? That question will ripple forward, touching minds like Louis de Broglie and Erwin Schrödinger, who begin to see that the rules might be even more fluid than imagined. The boundary between wave and particle fades, and physics begins to hum with ambiguity. But in this chapter, let us pause with Einstein, gazing into the brilliance of a single photon, a thread of possibility tugged from the heart of the sun. His work on the photoelectric effect earns him the Nobel Prize in 1921, not for relativity, not for his grand cosmic symphonies, but for this one quiet, radiant insight. It is fitting, because while relativity redefined motion and time, the photon redefined light itself. Picture a quiet pond at dawn. You toss a pebble into its still surface, and gentle ripples spread outward, graceful and predictable. This is the image we hold of waves, a continuous spread of motion, an echo that touches places far from its origin. Now imagine a marble, solid and definite. You throw it, and it rolls across a table, following a clear path. This is the image we hold of particles, localized, with mass and momentum, moving like little messengers through space. Two clean ideas, two separate worlds. And for centuries, physics kept them apart. Waves belonged to sound and light, particles to matter and mechanics. But quantum theory, ever the mischief maker, slowly dismantled that division. In the early 20th century, light had begun to behave strangely. As Einstein showed with the photoelectric effect, it could act as if made of discrete packets, photons, despite all evidence of its wave-like elegance. Still, many thought this duality was an odd quirk of light alone. Surely, matter, tangible, weighty matter, must play by the old rules. Then came Louis de Broglie, a French aristocrat turned physicist with a curious hypothesis. If light, once considered a wave, could display particle-like behavior, could matter, particles, exhibit waves? In the silence of the quantum, there are no firm boundaries, only shifting dances, waves that sometimes become particles, particles that ripple like waves. Think of your own experiences. Are you always a single thing? Or do you shift, fluid and responsive, depending on how you're seen, what you encounter, where your focus drifts? The universe, it turns out, is far more like us than we thought, mysterious, layered, and strange. Wave-particle duality was one of the first signs that quantum physics would not merely adjust our understanding of nature, but dissolve and rebuild it altogether. It's the kind of revelation that humbles even the most confident mind. The wave fades, the particle lands, and you drift peacefully into the in-between. By the mid-1920s, the quantum world had revealed itself as slippery and paradoxical, a realm where particles moved as, if uncertain, and waves whispered through objects once thought solid. Scientists stood at the edge of comprehension, watching mystery flow beneath the surface of certainty. And into this unfolding silence walked Erwin Schrödinger, an Austrian physicist, who didn't so much crash through quantum theory as threaded into a tapestry, where others grappled with fragments and flickers. He sought something continuous, something graceful. He longed for an equation, not just any equation, but one that could describe how quantum objects evolved in time, something like Newton's laws, but for the uncertain, dreaming realm of electrons, photons, and possibilities. And so, in a small alpine cabin in the winter of 1925, surrounded by snow and solitude, Schrödinger began to imagine what that might look like. He had been inspired by Louis de Broglie's wave hypothesis, the idea that particles had wave-like behavior. If matter behaved like a wave, it ought to follow a wave equation, just as ripples on water or vibrations on a string did. But what kind of wave was this? Where was it? What did it mean? After weeks of thought and a few false starts, Schrödinger found it, a mathematical expression that could describe the behavior of quantum systems with astonishing precision. This was Schrödinger's equation, not a thunderclap of revelation, but more like the unfolding of a flower no one had noticed growing. What does it describe? Not the location of a particle, exactly, not its momentum or its shape. Instead, it describes a strange and subtle concept, the wave function. This wave function, often represented by a Greek letter, is like a ghost. It holds within it all the potential outcomes of a system, where a particle might be, how fast it might move, what states it might assume. It is not the thing itself, but the mist of what it could become. Imagine holding a cloud in your hand, one that doesn't obey the usual rules of form. Now imagine that cloud represents a particle, not as a point, but as a field of probability. Schrödinger's equation tells us how that cloud changes over time. You can feel the world stirring, faint motion in the leaves, a gentle breath in the grass, but the whole scene hovers in uncertainty, not yet defined. This is where we find ourselves in the quantum world, not without knowledge, but with knowledge that hums just out of reach. It was in this delicate dawn that Werner Heisenberg, a young physicist shaped by both precision and curiosity, glimpsed something remarkable. In 1927, he proposed that there was a limit not only to what we do know, but to what we can know. At the heart of this idea is a pair of partners, position and momentum, where something is and how fast and in which direction it's moving. In classical physics, if you wanted to track a tennis ball mid-flight, you could measure its position and momentum as precisely as your tools allowed. Sharpen your instruments, reduce error, and you inch ever closer to perfect certainty. But in quantum mechanics, the game is different. Heisenberg proposed that the universe itself resists such precision, that the more accurately you try to pin down a particle's position, the less accurately you can determine its momentum, and vice versa. It's not a flaw in our tools. It's a feature of nature, a boundary painted into the fabric of reality. This is the uncertainty principle, and though it sounds almost poetic, it's as real and inevitable as gravity. But what does it mean? Imagine you shine a light on an electron to see where it is. In doing so, photons bounce off the electron and reveal its location. But those very photons also disturb it, nudging it, changing its momentum ever so slightly. The act of observing becomes an act of interference. This isn't just about electrons. This is about the foundation of knowledge itself. In the quantum realm, observation is participation. You cannot know everything about a system at once, because the knowing becomes part of the system. The uncertainty principle tells us that reality is soft around the edges, that precision has a cost, that trying to grasp both the where and the how of a quantum object simultaneously is like trying to hold a soap bubble between two hands. Press too hard, and it vanishes. Some tried to resist this idea. Einstein, ever the champion of determinism, famously remarked, "God does not play dice with the universe." He couldn't accept a reality built on limits to knowing. But Heisenberg and others saw it not as disorder, but as a new kind of order, an order woven from probability rather than predictability. This shift changed everything. It meant that electrons don't orbit the nucleus like planets around a star. Instead, they exist within blurred, Clouds of probability, fuzzy zones, where they're likely to be found, but never fixed in place. It meant that particles might tunnel through barriers, as if borrowing certainty from the future. It meant that the universe, at its core, behaves more like a poem than a machine, full of nuance, rhythm, and ambiguity. And beyond its scientific implications, the uncertainty principle echoed quietly into philosophy, art, and even psychology. Think of how we perceive others, a friend, a stranger, a self. The more closely we examine, the more elusive the essence can become. Identity isn't pinned down under scrutiny. It's revealed in motion, in interaction, in the spaces between. Heisenberg's insight reminds us that not knowing is not the same as ignorance. Sometimes, uncertainty is the deepest kind of truth. In the world of particles and waves, it is not about choosing one description over another. It's about accepting that both are incomplete until witnessed, that the dance only becomes visible when we step onto the floor. Imagine walking toward a locked door. According to every physical law you've ever obeyed, you should stop at the threshold, bounce off, turn away. But now imagine, impossibly, that without a key, without even touching the handle, you appear on the other side. This is not magic. This is quantum tunneling. In the ordinary world, we think in certainties. A ball rolls up a hill and slows to a stop. A train does not pass through a mountain. It waits for a tunnel or is stopped entirely. Barriers are solid, impassable. But in the quantum realm, particles are not little billiard balls. They are waves of possibility, draped across time and space. And when these waves encounter a barrier, a hill too steep, a wall too high, they don't always stop. They leak. This leaking is not a flaw. It's a feature of the mathematics that governs quantum behavior. The particle's wave function doesn't cut off at the wall, it extends into it, fading gradually like an echo into silence. And sometimes, just sometimes, part of that wave continues out the other side. Not over the barrier, not around it, through. It's as if the universe, built from rules, allows for whispers of rebellion. Let's step back. In classical terms, a particle with less energy than a barrier should be trapped. Imagine a marble in a bowl. It rolls around the inside, but can't escape the rim. Now shrink that world to a subatomic scale. An electron trapped in the potential well of an atom. But now, soften the boundaries. The electron isn't in one place. Its existence smears, described by a wave function that hums like a subtle bell. That wave doesn't stop at the edge of its container. It lingers, curling faintly into forbidden zones. And here's the miracle. That faint curl carries a tiny probability. Enough to mean that, unpredictably, unexpectedly, the particle might appear on the other side. It doesn't climb. It doesn't breach. It simply tunnels. This idea, strange as it seems, is not hypothetical. It's measurable, repeatable, and foundational to the physical world. Inside stars, for instance, atoms fuse together to form heavier elements. The process that lights the sun and breathes warmth into Earth. But fusion requires positively charged nuclei to come close, to merge. Yet their charges repel each other fiercely. Classically, they shouldn't reach each other. The barriers are too high, and yet they do. Quantum tunneling allows the particles to overcome their mutual repulsion and bind together against all classical odds. It is the secret handshake of the cosmos, written in probability. Closer to home, consider the modern miracle of microelectronics. Your smartphone, your computer, your flash drive, all depend on components so tiny, so precise, that tunneling becomes a factor. Electrons pass through insulating barriers inside transistors, tunnel diodes, and flash memory cells. Engineers once considered this behavior a problem, unpredictable noise. Now it's harnessed, controlled, designed. Quantum tunneling even shows up in scanning tunneling microscopes, devices so sensitive they can image individual atoms. By measuring the tiny tunneling current between a sharp tip and a surface, they map the ghostly contours of matter at its smallest scale. The more we learn, the more tunneling appears not as a rare exception, but as a quiet rule, hiding in plain sight, wherever probability nudges against impossibility. And yet, the wonder deepens. Some have speculated whether tunneling might explain phenomena not yet fully understood. How enzymes work with such efficiency, how quantum effects play roles in biology, even how particles might move between quantum states in the mind. Whether or not these dreams hold, the principle remains luminous. Tunneling tells us that barriers, even the most rigid, are not always absolute. That limitations are gradients, not cliffs. That the universe itself contains loopholes not of weakness, but of wonder. It reminds us, too, that presence is a spectrum. A particle is not here or there, but here-ish, there-ish, a shade of maybe until reality chooses. We are trained, from childhood, to choose. Is the coin heads or tails? Is the cat inside the room or outside? Is the light on or off? Binary thinking threads through human understanding like a well-worn path. But in the quantum world, where reality flutters instead of marches, the answer is sometimes yes. Yes to heads, and yes to tails. Yes to here, and yes to there. Yes, all at once. This is the essence of superposition, a principle at the heart of quantum mechanics, and arguably its most radical gesture. In the simplest sense, superposition means that a quantum system can exist in multiple states simultaneously, not as one chosen reality, but as a delicate blend of possibilities. Until measured, a particle is not this or that. It is everything it can be, like a chord yet to resolve into a single note. Let's begin with something small. A single electron can spin in one direction, up, or the opposite, down. In classical thinking, it must be spinning one way or the other, even if we don't yet know which. But in the quantum world, an electron can spin both ways at once. This is an indecision. It's inclusion. You observe, without consequence. A world that exists regardless of whether anyone is looking. But quantum mechanics whispers another truth. In this realm, a particle's state, its position, its velocity, its spin, is not settled until it is measured. Before that, it exists in a superposition, suspended in a blend of possibilities, all potential and no finality. Then a measurement is made, and the wave function collapses. Like 1,000 doors suddenly slamming shut, all but one path vanishes. This moment, this collapse, is the heart of the measurement problem. It asks, what exactly causes the collapse? Is it the measuring device? The observer's consciousness? Some hidden interaction? Or is it simply baked into the rules of quantum evolution? Physicists have tried to wrap this riddle in neat explanations, but it resists. Like fog beneath a lantern, the more you approach it, the more it recedes. Let's return, briefly, to Schrödinger's cat, that famous feline paradox. Locked in a box with a quantum trigger, the cat is both alive and dead in superposition, until observed. Upon opening the box, we witness one outcome. A choice is made. But what, exactly, constitutes observation? Is it the opening of the box? The moment photons scatter off fur and enter your retina? The instant a neuron fires in your brain? Some interpretations suggest it's not the observer that matters, but the irreversible interaction, the entanglement, between the quantum system and its environment. This is called decoherence. And while it elegantly explains how superpositions blur into classical outcomes, it still doesn't answer a deeper question. Why just one outcome? The wave function, according to the standard rules of quantum mechanics, evolves smoothly and deterministically until measurement occurs. Then, with no warning, it lurches into randomness. A sudden collapse. It is this chasm between the smooth unfolding and the abrupt selection that forms the core of the measurement problem. And from this chasm, many interpretations have emerged. The Copenhagen interpretation, long the most widely taught, claims that quantum systems don't have definite properties until measured. Measurement is an act of creation. The universe makes a choice only when compelled to. Then there's the many worlds interpretation, which refuses collapse altogether. When a quantum event occurs, it says, all possible outcomes unfold, each in its own branching universe. Open Schrödinger's box, and in one world the cat lives, in another it dies. Each version of you sees one result, but the multiverse sees everything. Measurement, here, isn't collapse, it's multiplication. Other interpretations, pilot wave theories, objective collapse models, quantum Bayesianism, offer their own answers, each elegant, each incomplete, none proven. The beauty, and the frustration, is that quantum mechanics works. Its predictions match experiments with mind-bending precision. It drives the digital age, powers MRI machines, defines the architecture of atoms. And yet, we don't know what happens during measurement. It's like using a spellbook that never fails, while never understanding what magic truly is. Beyond physics, the measurement problem ripples into philosophy, even into our conception of reality. If particles don't have definite properties until observed, what is the world, independent of our awareness? Is the moon there when no one looks at it? Einstein once posed that very question. And perhaps the deeper question, the one that sleep beckons you to ponder, is this: what does it mean to observe? Are we separate from the world we study, or part of it? When you look at a particle, does it notice you back? At a glance, the universe seems governed by separation. Objects occupy space. Events unfold locally. What happens here should not instantly affect what happens light years away, at least not according to common sense. But quantum mechanics has never been particularly fond of common sense. There exists a phenomenon so strange, so deeply unsettling to traditional physics, that Albert Einstein himself dismissed it as spooky action at a distance. He was referring to quantum entanglement, a gentle but profound tether that binds particles together in a way that defies space and time. To understand entanglement, let's return to a fundamental truth we've explored: quantum systems exist in superpositions, clouds of all possible states. Now imagine two particles created together, their properties delicately linked, like twins born of the same breath. Perhaps it's their spin, or their polarization, opposing in direction but undetermined in value until observed. Individually, neither particle has a defined state. They're both unresolved symphonies, but their connection is tight. If one resolves a certain way, the other must complement it perfectly. Now imagine separating them. One particle is sent to Tokyo, the other to Buenos Aires. Vast oceans and continents now stretch between them. And yet, when one is measured, the other's state becomes instantly known. It's not that one signal is sent and received. It's as if, in some quiet way, they never stopped being one thing. This is the mystery of entanglement, non-local correlation, a unity beneath separation. It's not just a thought experiment. Entanglement has been tested in laboratories with extraordinary care. Physicists have closed loophole after loophole, using entangled particles to prove that Bell's inequalities, mathematical expressions rooted in classical logic, are violated. The results leave no doubt. Nature is more interconnected than we ever imagined. Entanglement doesn't allow for faster-than-light communication. You can't use it to send messages instantly across space. But it does hint at something more astonishing: that the fabric of reality is not stitched together by distance alone, but by relationship, and the implications ripple outward. Quantum teleportation, once the stuff of science fiction, is now a reality in labs. Not the transport of matter, but the transfer of quantum information, perfectly reconstituted from one place to another, using entangled particles as a bridge. In quantum computing, entanglement is a vital ingredient. It links qubits together in ways that allow parallelism and complex processing far beyond the capacity of traditional machines. And in quantum encryption, entangled particles are used to detect eavesdropping with absolute certainty. Any attempt to observe the system breaks the entanglement, a whisper of intrusion, encoded in physics itself. But for all its utility, the poetic heart of entanglement may lie in what it suggests about wholeness. It tells us that separation is not always what it seems, that things once joined retain a kind of memory, a resonance that doesn't fade with distance, that information, even in silence, remains connected. In his resistance, Einstein hoped for a hidden mechanism, something beneath quantum theory that would restore order, clarity, cause and effect. But experiments have steadily shown that entanglement is not an illusion. It is a feature of the quantum world, not a bug. And so we sit with it. Odd. Two particles, one wave function, a dance that continues across time and space, not despite their distance, but regardless of it. And perhaps there's something deeply human here too. Haven't we felt it? A connection across miles, a bond unchanged by absence, a sense of being seen even when unseen. Entanglement whispers that perhaps the universe, like us, is defined not by isolation, but by intimacy. In the quantum world, particles blur into waves. Outcomes rest in probability, and observation carries consequence. But behind all this elegance lies a fundamental mystery. What is actually happening? That question, deceptively simple, opens the door to a hall of mirrors. The many interpretations of quantum mechanics. The mathematics remains the same, reliable and predictive. What differs is the narrative, the conceptual story we tell ourselves to explain what that math implies about the nature of reality. And no single interpretation has yet claimed the throne. Let us walk slowly through the most prominent perspectives, not to declare a winner, but to listen to how each voice describes the same deep music. 1. The Copenhagen interpretation, reality upon measurement. This is the oldest and most widely taught interpretation, shaped largely by Niels Bohr and his circle. It tells us that quantum systems exist in superposition, a blend of possible outcomes, but do not assume definite properties until measured. Observation causes the wave function to collapse, and one result becomes real. This interpretation is pragmatic, modest. It doesn't claim to describe what exists behind the veil, only what we can know. In Bohr's words, there is no quantum world. There is only an abstract quantum mechanical description. It is a kind of quantum agnosticism. What matters is the outcome, not the underlying truth. 2. Many worlds interpretation, all paths taken. Proposed by Hugh Everett in 1957, this view boldly denies collapse. Instead, it suggests that every possible outcome of a quantum event actually occurs, each in its own newly branched universe. Measure a particle, and reality splits. In one universe, you see outcome A. In another, outcome B. The wave function never collapses. It simply unfolds into an infinity of realities. In this vision, the cosmos resembles a vast, branching tree of possibilities. Your every choice, every quantum flicker, spawns a new version of you, walking a different path. Some find comfort in this interpretation, a deterministic universe without randomness. Others find it extravagant. Are we truly spawning entire universes with every glance? 3. Pilot wave theory, particles with hidden guidance. Also called the de Broglie-Bohm theory. This interpretation retains particles as real entities, each with definite positions and velocities. But their motion is guided by a wave, the pilot wave, that evolves according to Schrödinger's equation. Here, there is no collapse, no need for observation to create reality. The wave informs the particle's path, like a river current steering a leaf. It restores determinism to quantum mechanics. But at a price, it is non-local, meaning that one particle's behavior can be influenced instantly by distant conditions. Connection persists beyond space, much like entanglement. 4. Objective collapse theories, random collapse without observation. Some physicists dislike the idea that measurement alone causes collapse. Instead, these interpretations suggest that the wave function spontaneously collapses after a certain time or under specific conditions, independent of observation. The most famous model here is GRW, Gherardi, Rimini, Weber, which proposes that particles randomly collapse to definite states. For small systems, collapse is rare. For large, it's frequent, giving rise to the classical world we see. This model introduces randomness into the heart of physics, but removes the observer from a privileged role. 5. Quantum Bayesianism, reality as personal belief. Here, quantum mechanics is viewed not as a description of objective reality, but as a tool for agents, like us, to update our beliefs about future experiences. The wave function doesn't represent the world, it represents our expectations of it. In this view, there is no need for spooky connections or multiple worlds, just beliefs updated by data. It is humble, even radical, centering the observer not as a disruptor of reality, but as part of its unfolding story. And yet, beyond these major players, others linger in the wings: relational quantum mechanics, consistent histories, transactional interpretation. Each offers a lens, a metaphor, a way of speaking about a world that refuses to settle into a single tongue. What binds them is not agreement, but awe. Awe that the same mathematics, so concise, so precise, births such wildly different metaphysical landscapes. Each interpretation tries to answer the same riddle: how can a probabilistic, observer-sensitive model describe a universe that feels solid and objective? And perhaps the answer, whispered softly, is this: Maybe the quantum world is not unfinished. Maybe it is not illusory. Maybe it is greater than any one interpretation. A truth so rich, it allows itself to be understood in fragments, facets, and fables. Each morning, you awaken in a world that feels reliable. A coffee cup sits on a table. A bird glides past your window. You drop your keys, and they fall, not as a blur of probabilities, but as a solid object pulled by gravity. And yet, as we've wandered through this quantum journey, it's clear that underneath that smooth surface lies a stranger story. Particles live in superpositions. Observation affects outcomes. Entanglement defies distance. So why don't we see that? Why don't we experience chairs in multiple places at once? Or cats that live in ambiguous states of being? The answer is not that quantum mechanics gives way to classical physics at some arbitrary scale. The answer is decoherence. To understand it, let's return to the idea of a quantum system, say, a single electron existing in a superposition of spin states, alone in its isolated space. That superposition evolves gracefully, described by Schrödinger's equation. It's delicate, coherent, whole. But what happens when that electron interacts with its environment? Tiny collisions occur with photons, air molecules, other particles. Each interaction, however minuscule, leaks a bit of information into the world. The system, once wrapped in its own private superposition, now becomes entangled with countless invisible hands. These interactions are not dramatic. They don't resemble conscious measurement, but their effect is profound. Coherence begins to fade. The superposition doesn't vanish. Rather, it becomes dispersed. The different parts of the wave function, the this and the that of a quantum state, become so entangled with the environment that they can no longer interfere with each other. The once pristine quantum system now behaves as if it has chosen a state, though it never quite did. This is decoherence, the rapid loss of quantum clarity due to environmental entanglement, the subtle unraveling of the wave function's coherence, not through collapse, but through context. In practice, decoherence happens incredibly fast. For macroscopic objects, anything larger than a few atoms, interacting with the environment is unavoidable. The more complex the system, the more quickly its quantum character is blurred into classical behavior. Imagine a violin string vibrating in silence. Beautiful, sustained. But now place it in a noisy room. Footsteps, gusts of wind, distant traffic. Each vibration becomes harder to hear. The sound isn't silenced, it's washed out. That's coherence, drowned in interaction. So the classical world, the world we know and touch, isn't separate from quantum mechanics. It emerges from it. Decoherence is the bridge that connects the strange. Rules of the small to the familiar, rhythms of the large. And it's why, despite the quantum soup beneath everything, we live in a world of objects, choices, and memory. But decoherence doesn't just explain what we see. It also provides insight into what we lose. Quantum computers, for instance, rely on preserving superposition and entanglement across many qubits. But decoherence threatens that balance, causing errors and noise. Engineers build elaborate strategies to shield qubits, to keep them quantum just a little bit longer. In this sense, decoherence is not destruction. It's reconnection. The system stops being purely itself and becomes part of something larger, tangled within its surroundings. And perhaps there's beauty in that. We are, in a way, decohered beings, shaped by experience, by contact, by the worlds we've brushed against. We cannot return to isolated purity, but we gain something else: relation, context, story. Close your eyes and imagine nothingness. Not empty space, but a true void. No stars, no matter, not even time's breath. Silence so deep it forgets the sound of its own name. Now imagine that nothing trembles. Welcome to the world of quantum fields. Modern physics tells us that the universe is not, at its foundation, built from particles. Particles, electrons, quarks, photons, are excitations of something deeper: fields. These fields are not things that sit inside space. They are space. They are the canvas of existence, stretched across the cosmos like invisible silk. Each fundamental particle is born from its own quantum field. The electron field fills all of space. The quark field too. And the photon? Just a ripple in the electromagnetic field. What we call particles are simply localized disturbances, like tiny notes plucked from the silent string of the vacuum. In this view, the vacuum is not empty. It is alive. Even in the deepest reaches between galaxies, these fields persist, fluctuating ever so slightly in a restless dance. This is quantum vacuum energy, not silence, but a symphony played so softly that we mistake it for nothing. Imagine throwing a pebble into a still lake. The ripple is a particle. The lake is the field. The ripple moves, interacts, fades. But the lake remains, serene yet vibrant. These quantum fields interact according to rules we've come to know as the standard model of particle physics. Qubits are delicate. They must be isolated from noise, heat, and even stray vibrations, lest their quantum character decohere, collapsing into classical certainty. This makes quantum computers incredibly difficult to build and sustain. They require near-zero temperatures, precise control systems, and error correction techniques unlike anything used in traditional devices. Still, the quest advances. Quantum processors built from trapped ions, superconducting circuits, photons, and even topological states are being explored across labs and companies worldwide. Each approach has its quirks, but all seek the same goal: to unlock computations that were once impossible. So what could these machines do? Certain problems, in theory, are exponentially accelerated by quantum algorithms. For example, Shor's algorithm could factor large numbers with astonishing speed, potentially reshaping encryption and digital security. Grover's algorithm could search unstructured data far more efficiently than classical methods. Complex simulations of quantum systems, molecules, reactions, materials could become realistic, revolutionizing fields from drug discovery to materials science. But it's not just about faster answers. It's about new questions, problems we couldn't even phrase properly in classical logic, may find form in the quantum tongue. In that sense, quantum computers are not successors to classical ones. They are companions, reaching where classical logic cannot, illuminating edges too murky for binary light alone. Still, practical quantum supremacy, where a quantum computer clearly outperforms any classical system on useful tasks, remains an evolving challenge. Experimental achievements have demonstrated specific feats, but the road to general purpose, fault-tolerant quantum computing, is a long one. And yet, even now, in these early hours, the landscape feels electric with possibility. To think with qubits is to accept uncertainty as a tool, not a flaw. To process not just data, but probability itself. To ask the universe a question in its own language, one built not from static truths, but shifting spectrums. And somewhere in that spectrum, new ways of understanding may bloom. In fiction, teleportation is dazzling. A person vanishes in one place and instantly reappears in another. In physics, the story is stranger still, subtler, more precise, and infinitely more beautiful. Quantum teleportation doesn't involve moving matter. No atoms are broken apart. No molecules reassembled elsewhere. Instead, what's transferred is information, the abstract essence of a particle's quantum state, passed from one location to another without physically traveling the space between. To grasp this, we must first return to entanglement, that mysterious link, binding two particles in perfect harmony. Once entangled, their states are no longer independent. Measure one, and the other is instantly affected, regardless of distance. In other words, local realism, the comforting idea that things are what they are, independently of when or how we look at them, and that cause and effect flow cleanly through space, is not how the quantum world works. Quantum mechanics predicts correlations between entangled particles that no local hidden variable theory can reproduce. And nature agrees. Yet this isn't about faster-than-light messaging. No signal travels. No message is sent. And still, the measurement outcomes remain mysteriously coordinated. It's not communication. It's coherence, like a script written across distance, read aloud by particles in separate places, as if guided by a deeper unity. So what do we make of this? Some interpret it as evidence that the universe is non-local, that space and time are not as separable as they seem. Others explore interpretations where the wave function never collapses at all, or where measurement simply reflects shifts in our knowledge, not in reality itself. But what's undeniable is this: Bell's theorem transformed quantum weirdness from a philosophical puzzle into an experimental truth. Einstein called it spooky. But perhaps spooky is just another word for unfamiliar. Physics, at its heart, is a pursuit of unity. Throughout history, scientists have chased the dream of simplification, of finding patterns beneath complexity, of discovering that what seems distinct is merely the same truth in different dress. Electricity and magnetism became electromagnetism. Space and time merged into spacetime. Matter and energy revealed themselves as twins. But one great rift remains: the chasm between quantum mechanics and general relativity. Quantum mechanics governs the subatomic, a realm where probability and uncertainty reign. General relativity describes the grand curvature of space and time, where mass tells spacetime how to bend, and spacetime tells mass how to move. Each is majestic, each is exquisitely precise, but together, they fracture. Try to describe a black hole's singularity, a place of infinite density, and general relativity predicts the collapse of geometry itself. Bring in quantum mechanics, and the math breaks into contradiction. Time ceases to be smooth. Space loses coherence. Cause and effect begin to stutter. This, then, is the dream of quantum gravity: to weave the probabilistic rules of the quantum with the geometric fabric of gravity, to craft a single framework that includes both. But where do we even begin? One path is string theory. It proposes that particles are not points, but tiny, vibrating strings. Different modes of vibration give rise to different particles, an elegant idea, like notes plucked on a cosmic violin. In this framework, gravity isn't added on. It emerges naturally from the math. The graviton, the hypothetical quantum of gravity, appears as one such vibration. But string theory requires extra dimensions, hidden and curled beyond our perception. It suggests a multiverse of possible universes, each with its own physics. Some call this freedom. Others call it an escape. Another avenue is loop quantum gravity, a more minimalistic approach. It tries to quantize space itself. In this view, spacetime is not smooth, but granular, made of tiny loops, woven into an invisible lattice, like threads in a quilt too fine to see. At this scale, geometry becomes a kind of quantum state, fluctuating and uncertain. These theories, and others, remain incomplete. Beautiful, yes. Promising, often, but experimentally unproven. And yet, nature may already whisper clues. The early universe, just moments after the Big Bang, operated under conditions where quantum gravity would have ruled. Black holes, with their warping of space and absorption of information, may be laboratories for quantum gravitational effects. And the great puzzle of dark energy, which drives the universe's accelerated expansion, might someday connect to the quantum properties of the vacuum and the structure of gravity itself. Even time, so seemingly solid, may not be fundamental. Some theories suggest that time emerges from entanglement and correlations, not as a ticking background, but as a relational property between systems. It's humbling to realize we do not yet know what space is, or time, or gravity. We are like fish trying to define water, unaware it is the medium through which we move. But the search continues. Experiments grow more sensitive. Space-based observatories, underground detectors, and deep theoretical insights all inch us toward the bridge. And in this search, something more than physics pulses beneath. A longing to know not just how the world behaves, but what the world is. To find a language where Schrödinger's equations and Einstein's field equations are not rivals, but verses of the same poem. A poem that speaks of curves and quanta, of ripples and loops, of gravity and dream. We live in the grip of assumptions. That time flows forward like water down a slope. That causes precede effects. That reality exists, solid and indifferent, whether or not we observe it. But the quantum universe asks us, politely, unsettlingly, to let go. It begins with time. In the classical world, time is a river, with each moment following the last, neat and sequential. Newton saw time as absolute, the same for all, ticking steadily in the background. Einstein redefined it as relative, bound to motion and gravity, intertwined with space. But quantum theory? It doesn't quite know what to do with time. In Schrödinger's equation, time is not an observable. It isn't represented by an operator like position or momentum. It's external, a parameter, not a player. The wave function evolves over time, but time itself is untouched, as if drawn from a clock outside the universe. This mismatch creates deep tension, because if quantum theory is truly fundamental, if it applies to everything, then why should time be separate? In a truly quantum universe, shouldn't time also be quantum? Nowhere does this question scream louder than in quantum gravity, where space-time itself must be subject to quantum rules. But in some formulations, time disappears altogether from the equations. What's left is not a flow, but a structure, correlations between things, without a universal now. In such a view, time is not something the universe has. It's something that emerges from entanglement, from observation, from change. Which brings us, naturally, to causality. We like to think that causes come before effects, that action leads to consequence. Light the match, and the candle glows. But quantum mechanics slips loose from this ordering. In experiments involving entangled particles, measurements taken seemingly after an event can influence outcomes that look to have come before. The effect doesn't rewrite the past, but it suggests that causal direction is not absolute. More recently, researchers have devised experiments where the order of events becomes indefinite, a quantum switch, where process A happens before process B and process B happens before process A, not alternately, but simultaneously, like a logic not refusing to untangle. Causality, it seems, might not be fundamental. It might be contextual, woven from interaction, not imposed from above. And this leads us, finally, to the deepest pool, reality itself. What exists when no one is looking? If a quantum system remains in superposition until observed, until measured, what does that say about the world before measurement? Some interpretations, like Copenhagen, sidestep the question. Others, like many worlds, insist every possibility does occur, each in its own branching universe. Still others, like relational quantum mechanics, suggest that properties are not absolute, but relational, existing only between systems, like ripples shared between shores. Reality, then, may not be a fixed landscape. It may be a web, spun not from certainty, but from interaction, correlation, and perspective. Perhaps existence is not a monologue, but a conversation. Not a static sculpture, but a symphony played anew with each listener. There is one more twist to ponder. The quantum universe, with all its ambiguity, its riddles, its refusal to bow to common intuition, still gives rise to the classical world we know. Apples still fall, clocks still tick, people grow old. But beneath this surface lies a realm of breathtaking strangeness, where time may be an echo, causality a habit, and reality a question folded quietly into the act of being. What does it mean to live in a universe governed by quantum principles? For much of our daily lives, the classical world feels unshaken. Cars roll down streets. Coffee cools predictably. Hearts beat in rhythmic certainty. But beneath this surface of reliability lies a humming, probabilistic undercurrent. And once you've glimpsed it, it's hard to look away. Because quantum mechanics doesn't just describe small things. It questions everything. And in doing so, it draws us into the deepest philosophical waters about knowledge, about mind, about what it means to exist, the observer and the observed. Quantum mechanics shattered the old idea of objective, detached observation. In experiments like the double slit, the simple act of measurement shifts reality's unfolding. A photon's behavior changes not with the presence of a screen, but with our awareness of it. What does this say about the role of consciousness? Some have proposed that conscious observation might be the key ingredient, the agent that collapses the wave function, that turns possibility into actuality. This is the view tied, though often debated, to interpretations like von Neumann, Wigner, where consciousness plays a central role in shaping outcomes. Others push back. It's not consciousness per se, they argue, but interaction. Any irreversible entanglement with the environment can induce decoherence, collapsing the quantum state into classical clarity. Still, the question lingers. Why is our perception so pivotal? It may be less about consciousness altering reality, and more about the impossibility of extracting ourselves from reality. We are not separate observers. We are participants. Reality is not written behind glass. It is lived, continuously reassembled through experience, and relation. Is the universe mindful? Quantum strangeness has led some to speculate that consciousness isn't an emergent byproduct of complexity, but a fundamental ingredient of existence. Philosophies like panpsychism suggest that consciousness, in some form, may pervade the cosmos, not as thinking minds and atoms, but as a primal quality, like mass or charge. Others imagine a quantum mind, where the brain's synapses and microtubules may tap into quantum coherence. Though such ideas remain controversial and unproven, and yet, even without certainty, we return to the poetic resonance that perhaps reality isn't a cold, indifferent clockwork, but a flowing conversation, that the universe might not simply exist, it might experience meaning in the midst of uncertainty. Quantum mechanics replaces absolutes with probabilities, predictions with potentials. For some, this unsettles. It defies our desire for a universe that's ordered, understandable, deterministic. But in that unpredictability lies something human. We, too, are uncertain creatures, capable of holding contradictions, dreaming futures that haven't arrived, becoming more than what came before. To live in a quantum world is to live poetically, accepting that not all truths are fixed, and not all questions resolve cleanly. It means we are shaped by context, not isolation. What is real may also be relational. The future isn't written, it's woven. Certainty is overrated. Wonder, perhaps, is not. In the end, perhaps the lesson of quantum mechanics is not that we are insignificant, but that we are entangled with each other, with the cosmos, with the mystery beneath it all. We are not outside the equation. We are written into its very form. Thank you for watching.